So it's great pleasure to introduce next speaker, Anatoly Dymarsky from University of Kentucky, and Caltech, sorry, and he'll tell us about quantum dots and conformal field theories. Please.
Yes, thank you to the organizers for putting together this great conference. I'm very happy to speak about my recent work connecting classical and quantum codes to conformal field theories. This is a new topic. To the extent I know the connection between quantum codes and conformal field theories, the explicit connection, have not been outlined before. And therefore, my talk mostly will be an introduction to the codes. The biggest part of my talk will be simply an introduction to a theory of classical and quantum codes. And then I will outline the basics of the construction, how to connect those codes to CFTs. And then maybe toward the very end, the last 5 minutes of my talk, I will very quickly speak about applications. And there are two kinds of applications. One can try to use codes to construct a conformal field theory with some special properties. For example, a CFT with a given value of central charge and maximal value of spectral gap. You can try to do that. And along these lines, this is very much related to the modular bootstrap program, which tries to bound certain properties of conformal field theories numerically. And then there is another line of applications when you try to use codes to study properties of the ensemble of theories. I will say a bit more words toward the end of my talk, but the idea here is that there is a new version of holographic dictionary where you relate gravity in the bulk, not to a particular conformal field theory, but to an ensemble of conformal field theories. And therefore, properties of the ensemble is becoming something very important, something which you need to understand. And code theories provide a very approachable playground to test different ideas, because the ensemble of code theories is algebraically much simpler than the ensemble of all CFTs or an ensemble of other kinds of CFTs. Okay, let me start with the introduction. What is a code? I will be speaking first about simplest possible codes, namely classical linear binary codes. A mathematical definition would be that a linear classical binary code is a vector space of dimension k over the field F2 or over the field Z2. Field F2 or Z2, it's a field which consists of two elements, 0 and 1. If I prefer not to use this sophisticated mathematical language, and instead of saying that something is over field F2, you can simply say that you do algebra the very usual way you do algebra, but in the end of the story, you only consider things modulo 2. So you have integer numbers and you only care if they're even or odd. So I gave a formal definition, some sort of vector space, but since my field is not continuous, it's not real numbers, it's not complex numbers, this is this field Z2, the properties are very, very different. Let me build some intuition by giving you an example. A classical code is simply a bunch of binary strings. This is shown over here. It's a bunch of binary strings of a particular length. Length n, that's a number of elements of the binary string. That's sort of the dimension of vector space into which you embed your code. And then you also have a total number of linearly independent strings which form a basis of your code. So in this case, I wrote just two binary strings, 0, 0, 0 and 1, 1, 1. Obviously, they form a vector space. If you add them to each other, you don't get anything else, because remember, we always work modulo 2. So this is the simplest possible code. So the code is parameterized by three numbers. One number, n, is the number of elements. That's sort of the dimension of vector space into which you embed your code. K is the number of linearly independent code words. In this case, this is just one independent code word. This is a trivial code word. It is always there because the code is a vector space, and vector space always includes 0 vector. And then the third number which characterizes a code is what is called the Hamming distance. And to explain what Hamming distance is, I would rather try to explain, visualize what code is using pictures. Instead of using algebraic approach and saying that code is a vector space, I will say that each binary string of this form labels through the conventional way a point on a unit cube. Since each entry is either 0 or 1, it means that each binary string of length n denotes a vertex on a unit cube in n dimensions. So the code I have written here, which consists of these two code words, corresponds to two highlighted vertices on a unit cube in 3 dimensions. I think it is self-explanatory. So what is the Hamming distance? Hamming distance is the following property of a code. You fix the origin, that's the trivial code word, and then you try to understand what's the closest highlighted point to the origin. And the distance between the closest point to the origin is the quality of the code, if you wish, and it's called the Hamming distance. In this case, this distance is 3, but by saying distance, what I actually meant is length squared, Euclidean length squared. Euclidean length squared is the correct way to denote distance because it also corresponds to the number of flips. You need to take one vector and make it another vector. So to go from this vector into this vector, you need to change the value of 3 letters or 3 elements, or how people say it in information theory, you need to flip 3 bits because each element is a bit. So this particular code has characteristic 313. That's standard notations. Okay, now the code theory is a well-developed mathematical theory, but many central, most fundamental questions about code theory are not well understood even now. And one of those questions is how to build a good code. A good code is a code which will have minimal distance between origin and the closest point to it as large as possible. Of course, it's easy to do if you have very few highlighted points. If you have only 2 highlighted points, just put them on the opposite parts of the cube and you're done. But the idea of having a good code is the idea that you try to maximize D and try to maximize K simultaneously. A code with a characteristic K, which has K linearly independent code words, has 2 to the K highlighted vertices. And basically what you're trying to do, you try to take a cube in many dimensional space. You try to highlight as many vertices as possible, but you try to keep all of them far away from the origin. And this is very difficult to do because your points form a vector space. And basically, as soon as you try to highlight more points, at least one of them will come closer to the origin. So the idea of maximizing K and maximizing D simultaneously, they're in conflict with each other. And how to properly do that, we still don't know. And we don't know the bounds. Let's say when you keep K divided by N fixed and you take N to infinity, we still don't know what's the best D you can achieve. Okay, so this is like the most basic thing about codes. Once you define codes, you can characterize them algebraically using what is called the polynomial. What is the enumerator polynomial? What is this polynomial? This polynomial encodes information about the spectrum of the code. The spectrum of the code, geometrically, is simply the total number of lengths from the origin of a cube on the previous slide, from the origin to the cube, to all highlighted points you have. You have 2 to the K minus 1 highlighted points except for the origin, and you try to keep 2 to the K minus 1 numbers, which are distances between origin and those points. And it's convenient to do that by writing a polynomial in terms of auxiliary variables. And then if your code satisfies certain nice properties, then this polynomial will also satisfy certain nice properties. Since my vector space naturally is equipped with the scalar product, you can introduce dual code by saying that as a vector space, it's a dual vector space. And then since the field you are working over is a discrete, since your field is a discrete field, Z2 is a discrete field, you can have something which cannot happen over field of real or complex numbers. You can have a vector space which is self-dual to each other, which means that you will have vectors which are self-orthogonal. That's okay, because basically the norm of the vector is the conventional norm squared, but mod 2. And therefore, if your norm is even, you equate it to 0. So in that sense, a vector could be orthogonal to itself. So you can have codes which are self-dual. And if code is self-dual, then a numerator polynomial will satisfy this rather non-trivial algebraic identity, which is called Mach-Williams identity. This is something which you can prove rather straightforwardly using a discrete Fourier transform. Okay, once we understood what codes are, let us try to discuss how to associate lattices to codes. That's a fundamental thing. That's the crucial thing in my talk. It's not new. I'm saying something which is very, very well understood mathematically. But if this is the first time you're seeing that, that might be something interesting. It's not difficult, but that might be something interesting because we rarely do things like that in physics. But the idea is the following. We have a code, and I was trying to explain that the code is a bunch of highlighted points on a unit cube. Here on a picture, I have two-dimensional cube. So two-dimensional cube is a square. I have two highlighted points. So they correspond to the code with two code words, 0, 0, and 1, 1. This is just for visualization purposes. And then in order to make a lattice out of this unit cube, what you do, you put this unit cube as a cube intercubic lattice, like in the picture. And then you take each red point, each highlighted point, and you move it in all directions with a step 2. You move it in all directions with a step 2. And after you move it in all directions with a step 2, you take another highlighted point and you also move it in all directions with a step 2. And all highlighted points on the red cube, you should move them in all possible directions with a step 2. This is what I did in this picture. And as a result, you have a periodic structure, which is actually mathematically a lattice. And the unit cell of this lattice is here highlighted in orange. So this procedure is written down here algebraically. You say that X is a vector with integer components, and this vector, so it's a vector in this cubic lattice, and this vector belongs to my new lattice associated with the code if and only if X modulo 2, which is a binary string, as a binary string, it would be a vector belonging to my code. So this formula is a manifestation of the procedure which I explained verbally a minute ago. Now, to complete the picture, to complete the construction, in principle, you need to take this vector X and rescale everything by square root of 2. I cannot do that on the screen, but you should mentally just try to take this picture and squeeze it a little bit. Why we want to do it? Because if you look at this unit cell here, highlighted in orange, we can very easily calculate the area of this cell. The area of this cell is, of course, equal to 2. And later on, we want to work with self-dual lattices. For self-dual lattices, cell should have a volume 1. And exactly to make this volume 1, you need to rescale everything by square root of 2. Okay, so at this point, let me reiterate. We started with classical codes. We learned how to visualize them by highlighting points on a unit cube. And then we learned how to define lattices for each linear code. Now, if you have a linear code with some special properties, you can be sure that the lattice would have special properties as well. For example, you can start with a lattice associated with a code and try to calculate something which is called theta series of a lattice. Theta series of a lattice is when you take a vector on a lattice and you sum over all lattice vectors, and for each lattice vector you calculate, you sum this exponent. It's an exponent of I tau x squared. And if your lattice is associated with a code, it means it consists of subsets. Each highlighted point on a unit cube, remember each highlighted point on a unit cube would give rise to this periodic structure in a two-dimensional space. So you can split the sum over here into sum over subfamilies. So for example, we first sum over this subfamily, and then we sum over this other subfamily, and each subfamily corresponds to vectors of the original code. And therefore, it's not a crazy idea if you resum things like that, that the result in the end of the story will be expressible just in terms of the code itself. And indeed, you can simply do this algebra and notice that the theta series of a lattice will be simply given, excuse me, by a numerator polynomial of a code, where instead of auxiliary variables x and y, you plug in Jacobi theta functions. So we immediately see that lattices associated with codes, they are nice because, for example, their theta series is very easy to calculate. Okay, now what if I consider classical code which satisfies the following property? It will be self-dual as a code, and it also will be double even. Double even means that the length of each code word is the name of the vector which belongs to the code. Each code word would have length divisible by 4. Excuse me. If you consider any code with these special properties, it turns out that corresponding numerator polynomial would satisfy these corresponding two identities. This identity is associated with the self-duality, and this identity is associated with the property of the code of being double even. But then the corresponding lattice, which we learned to build on the previous slide, would have the following two properties. It will be even and self-dual. And any even self-dual lattice defines a conformal field theory, which is chiral. And you can immediately calculate the partition function of this chiral CFT by calculating theta series of the corresponding lattice. And that in turn is expressible in terms of a numerator polynomial of a code. So basically, the CFT associated with the code would have a partition function which is simply given in terms of a numerator, polynomial which characterizes the code. Okay, so this is some simple results, some simple algebra. You can ask the following question. My conformal field theory must be modular invariant, which means that torus partition function, this is a torus partition function, it should be a function invariant under modular transformations of tau. Can I easily see that? There are two special modular transformations you need to worry about. One of them is tau goes into tau plus 1, and another goes into, another takes tau and maps it into -1 over tau. And you can very easily see that that invariance of Z under these two transformations is guaranteed by those two algebraic properties of W. So the punchline is the following. Modular invariance of Z is guaranteed by the algebraic properties of a numerator polynomial, which come from those two special properties of the code itself. So the story so far was about classical codes. And this story is actually not new. It has been known since late 80s and early 90s. What we did is we generalized the story to the quantum case. And then I will spend a few minutes to speak about quantum codes. And the quantum story of quantum codes starts completely differently because there are no vector spaces, there is nothing. Well, there is nothing simple. There is some quantum system, presumably consisting of n qubits, of n spins. And you try to encode some states in the Hilbert space, and that would define your quantum code. So what you usually do is the following. You have a system consisting of n spins, n qubits, and you try to define a subspace of Hilbert space, which you will call a code subspace. And this Hilbert subspace should have certain nice properties, which I will not explain in this talk to save time. But I will explain how you define this code subspace. You define certain unitary generators GI, and those generators GI, they form an abelian group, which means that they commute with each other. And then you try to find a subspace of all vectors which are invariant under the action of this abelian group. So in other words, your code subspace is the subspace of vectors in the physical Hilbert space of qubits, which is stabilized by some abelian group which you introduced. So since this subspace of Hilbert space is stabilized by this abelian group is conventionally called the stabilizer group, and the type of quantum codes designed this way are called stabilizer codes. So to be a little bit more formal, and for the reasons of computational simplicity when it comes to quantum computers and the attempts to implement quantum computers, people choose the generators of your abelian group in a very special way. You have n qubits, and you say that your generator of a stabilizer group is a tensor product of Pauli matrices, each acting on a particular qubit. So there are 4 Pauli matrices, the 3 conventional Pauli matrices and the identity. And those 4 Pauli matrices, you combine them in such a way that the strings of those Pauli matrices, there are strings of Pauli matrices, there are strings of Pauli matrices, and each string of Pauli matrices is a generator of an abelian group. And you want, since your group is abelian, you want those strings to commute with each other. So the formula here is the following. You parameterize each generator of an abelian group by a string Ci, and each element of Ci has one of the 4 values. Each value stands for either identity matrix or Pauli matrix X, Y, or Z. So there are 4 values. And it actually proves convenient to parameterize those 4 values by saying that each element of C is actually an element of a field F4. Field F4 has 4 components. So it's just enough to parameterize for Pauli matrices. And field F4 can be thought very conveniently as 4 particular points on the complex plane. This is point 0 and also 3 cubic roots of unity. One itself and then 2 other non-trivial roots of unity. And those 4 points, they form a field F4 if you additionally apply a constraint that 2x should be identified as 0, okay? So if you use these rules and you define F4 this way, then it will be, mathematically, it will be a set with 4 elements, and each element can be identified with corresponding Pauli matrices. That would be identity Pauli matrix, that would be X, Y, and Z. And then why this is a convenient parameterization? This is a convenient parameterization because if you take 2 generators of your stabilizer code, one is associated with the string S1, C1, and another is associated with the string C2, and you take a product of them, then you will get another generator which is associated with the string C1 plus C2. So basically, the mathematical statement, which is a trivial mathematical statement, is that the abelian stabilizer group, which is a group of unitary matrices built out of these Pauli matrices, this abelian group, as an abelian group itself, is completely equivalent to the vector space of vectors C, which are vectors in this, which are vectors with the elements in F4. Okay, so vector space can be understood as an abelian group, and there is a statement that the abelian group of these guys is equivalent to the abelian group of vector space C. So then mathematically you can say that your quantum code is simply some linear vector space with the elements in F4. And that defines quantum codes. Classical codes were codes with the elements only binary, and quantum codes, vector spaces with the elements in F4. And then the rest follows. You can also define a numerator polynomial, but now each letter of the code word, each element in your vector can have 4 components, and therefore your numerator polynomial must depend on 4 auxiliary variables. You can define scalar product, a notion of duality and self-duality. And if your code is self-dual, then you will have what is called McWilliams identity. I'm watching time. It will be McWilliams identity. but it's complicated one, but some algebraic identity. And then you can also have reality condition that all the generators of your stabilizer group as unitary matrices, they're actually real valued. So they will be not unitary, but orthogonal. And in this case, your enumerator polynomial will satisfy another identity. And sure enough, you can actually relate corresponding codes to lattices of a particular kind and to Narain CFTs. So before I explain how that happens, I remind you what Narain CFTs are. Narain CFTs are conformal field theories, two-dimensional, which describe n free fields, which are compactified on a torus. A torus is specified by a metric, and there is also B field on the torus. And it's very easy to show that such a CFT is associated in one-to-one correspondence with a particular type of lattices called Narain lattices. These are even self-dual lattices in the Lorentzian space Rn, n. And for each such CFT and for each such lattice, you can define partition function by essentially evaluating theta series. This time, this theta series depends both on Q and Q bar, or it means it depends on tau and tau bar. This is not the conventional chiral theta series. This is what is called Siegel theta series, generalized theta series. So now the rest is the following. We start with a quantum code, 4 elements, which are elements of a 4, 0, 1, omega, and omega bar. 4 elements can be mapped to 4 elements of Z2 cross Z2. So instead of having a string where each element of a string is an element of a 4, you have a binary string which with each element being 0 and 1. But now the string is twice longer. And then this binary string can be mapped to a lattice the usual way, how I explained in the beginning of the talk. And it turns out that this lattice will have nice properties. For example, if your code was self-dual, your lattice will be self-dual, but it will be self-dual with the Lorentzian metric. And if you combine your code to be self-dual and real, then the corresponding lattice will be Narain lattice, and you can define the CFT with this lattice, and the partition function of that CFT will be given just in terms of the code itself, namely in terms of the enumerator polynomial, and A, B, C, and D are particular, concrete, known combinations of Jacobi theta functions. So this is basically the main part of our construction. We started with the quantum codes. We understood them as classical codes over F4 or twice longer codes over Z2. And then we mapped them to lattices. And then we recognized that these are nice lattices, self-dual lattices, but not in the Euclidean space, but in the Lorentzian space with this signature n, n. And then we realized that instead of relating them to chiral CFTs, you should relate them to non-chiral CFTs. So that's basically our construction. Okay, I have finished with my introduction. I have, my talk is like 30 minutes plus questions, I suppose. So I have two minutes left. So let me speak about the results. You can try to use this construction to study particular types of CFTs, and CFTs obtained this way, we call them code CFTs. So first of all, the main result we have is that quantum codes define a special subfamily of Narain CFTs, which we call code CFTs. The mathematical thing which I did not explain is that those code CFTs can be conveniently parameterized by graphs. That comes from the fact that codes themselves can be parameterized by graphs. And then by enumerating graphs carefully and understanding the equivalence conditions between graphs, you can actually say what kind of non-equivalent CFTs you have. And then we have very simple way to build theories with interesting properties. For example, you can build many dozens of examples of physically distinct conformal field theories, which have exactly the same physical spectrum, which means that they will have exactly the same spectrum of operator dimensions. And that example generalizes what is called the Milner's example of two isospectral Euclidean lattices. And then another application we had basically this formula, which evaluates CFT partition function in terms of a numerator polynomial, you can understand it as some simple ansatz which reduces modular invariance of CFT partition function to some algebraic identities which are easy to solve. And in that sense, what we are introducing very, very simple ansatz to solve modular bootstrap constraints. And you can see that among the theories we constructed, there are what is called optimal theories, meaning there are theories which maximize the value of the spectral gap. They maximize the value of the dimension of the lattice non-trivial operator for particular values of central charge. And besides that, we also have examples of fake partition functions, fake in a sense that we can give you an explicit expression for the modular invariant function z, which has all the properties you expect from the CFT partition function. It starts from identity. It has, well, in proper notations, it starts from identity. The coefficients in front of powers of q are integer. So in all possible senses, that could be a partition function of a real CFT. But in fact, we do not have any CFT to claim this particular z as its partition function. I'm stopping short from saying that we prove that there are no such CFTs, but we don't have such a CFT in a sense that our construction doesn't give you such a CFT. It gives you z by solving algebraic constraints at the level of polynomial w, but we know that there is no code associated with this w, and since there is no code, there is no CFT according to our construction. There might be some other construction, there might be some other hypothetical CFTs, which would claim this z as a partition function, but that is still an open question. Okay, so these are applications toward modular bootstrap and toward CFTs with some special particular properties. I think I ran out of my time. I would need to ask the organizers, the session chair, if I have another minute or two to speak about other results, or I should wrap up at this point.
If it is 1 minute, that's fine. Please go.
That's fine. Okay. So another application which I just want to sketch is the application toward holography. More recently, people started discussing a new version of holography where quantum gravity is dual not in ADS, is not dual to a particular CFT, but dual to an ensemble of CFTs. And if you just think about it for a second, if you want to have an ensemble on a CFT side to be dual to something classical in the bulk side, that already creates some interesting tension because classical description in the bulk, by its definition, by classical theory doesn't have variance of any observable. Any observable is well defined. But if you have an ensemble on another side of the duality, by definition of an ensemble, you have variance because different elements of the ensemble have different properties and you have variance. So how is it possible that you will equate ensemble to something classical, at least in the leading central charge to infinity order, and so on and so forth? That's only possible if your variance is vanishingly small. So I'm, of course, jumping over and skipping many things, but I'm trying to outline the question. If you want this new way of duality to work, you need to make sure that the variance is small. And we really lack any intuition of how that would work. So here, code theories come handy because code theories come with an ensemble. They come as an ensemble. You have many, many codes, exponentially many codes. Those form the ensemble, and therefore you can discuss properties of that ensemble. And that's what we did recently, and we calculated, basically we calculated variance of the density of states in code CFTs. That's what we did in the end of 2020, in the December of 2020. So we did not consider all Narain CFTs, we only considered certain subfamilies of CFTs and basically reduced things to codes. And in that particular example, we were able to show that the variance is exponentially small, which we think is a generic prediction. So this formula gives you an idea how this duality might work. You do have variance on the ensemble side, but it is exponentially small it becomes vanishingly small when central charge becomes large. So that's how your classical theory could be dual to something non-trivial on the CFT side. Now I'm skipping all the details. Oh, this is the wrong slide, oh no, this is the right slide. This is the conclusion slide. This is the conclusion slide. So I'm skipping all the details, but let me reiterate. So we introduced the novel connection between quantum codes and conformal field theories, and we have used it to study CFTs with some special properties, and we have used it as an ansatz to solve modular bootstrap equations, which is one line of applications. And there are many other questions which can be studied along this way. But then there is another application, which I only briefly mentioned toward the end. And another application is the following. A relation between CFTs and codes gives you a very natural toy models to study ensembles and the properties of the ensemble. And as the simplest property of the ensemble, for example, we calculated variance of density of states, and it happens to be exponentially small, which we believe is the avatar of how things work more generally. So whenever you want to have a holographic duality, you must have something like that on your ensemble side. There are, of course, fundamental questions remain here in this whole story. One fundamental question is the physical meaning of quantum codes. We algebraically related them to CFTs, but CFTs themselves are quantum. They have Hilbert space and so on and so forth. So the question is, if there is any physical meaning of quantum codes when it comes to CFTs, and if there is any relation to holography, which is more elaborate than what we discussed so far. And another important question, a fundamental question, is if our construction in some ways can be extended beyond Narain theories. There are many other interesting CFTs without Narain symmetries, without lattices, just Virasoro symmetry, and that's all. And the question is, can you define something like code in that context? Of course, these are very big questions. They remain open. They remain as a motivation for future research. Thank you very much.
Thank you. Thank you very much. So we have time for one question, and then we turn to a discussion session for all speakers. So question for Anatoly. Oh, we are ready to start discussion session.
May I have one short question?
Okay, so please.
Thank you for talking, Anatoly. So just from naive expectation, what will change if you consider not a CFT, but a boundary CFT and apply this error correction black magic?
I honestly don't know what will happen. The construction I have is not to start from CFTs and reduce it to codes. The construction the other way around. We start with certain codes and we manage to relate them to certain CFTs. I can interpret your question this way. If there are any codes which I might try to relate to boundary CFTs,
yes.
I do not know. That's an interesting question, but of course I do not know the answer.
Okay.
All right. Okay. Thank you very much. So now let's thank again Anatoly, and now it's time for discussion session. So questions to all speakers this morning session.